This paper examines hallucination in LLMs from a theoretical perspective. While numerous empirical studies have attempted to mitigate hallucination, no prior work has formally addressed whether it can be eliminated entirely. The authors create a formal framework to prove that hallucination is inevitable for any computable LLM, regardless of architecture, training method, or dataset used. The authors construct a formal world where hallucination is defined as inconsistencies between a computable LLM's output and a computable ground truth function. They define an LLM training procedure that can use arbitrarily many training samples, making their framework more general than real-world LLMs. By applying diagonalization arguments from learning theory, they prove that no computable LLM can eliminate hallucination completely. This figure illustrates how LLMs operate within the formal framework. The real-world corpus contains the formal world defined by a computable ground truth function. LLMs are trained iteratively on samples until stopping criteria are met, then deployed to produce outputs for unseen inputs. Hallucination is measured by comparing the LLM's answers with ground truth values. This framework captures the essential dynamics of real-world LLM training and deployment. The authors prove that for any computably enumerable set of LLMs, there exists a computable ground truth function that causes all LLM states to hallucinate. The proof uses a diagonalization argument to construct a ground truth function that explicitly contradicts any given LLM on specific inputs. Even more strongly, they show LLMs will hallucinate on infinitely many inputs, not just a few edge cases. This result applies to all real-world LLMs, which are bounded by polynomial time complexity. Building on earlier theorems, the authors prove that any individual computable LLM will inevitably hallucinate on some ground truth function. A specific example shows LLMs cannot learn all computable linear orderings, demonstrating practical implications. Importantly, Corollary 1 states that LLMs cannot eliminate their own hallucination. Methods like chain-of-thought reasoning cannot overcome this fundamental limitation. These results are independent of implementation details like architecture, training procedure, or prompting techniques. The table identifies specific problem classes where hallucination is guaranteed. Current LLMs are polynomial time-bounded, making them prone to hallucinate on problems requiring exponential or greater computational resources. This includes combinatorial listing tasks, NP-complete problems, assuming PNP, and problems requiring even greater computational resources, like Presburger arithmetic. Empirical studies confirm these theoretical predictions. LLMs consistently fail on these problem types regardless of size or training. This work proves that hallucination is an innate limitation of LLMs, not just an engineering challenge to overcome. While external aids like knowledge retrieval can help for specific tasks, no LLM can be hallucination-free as a general problem solver. The authors emphasize that LLMs should not be deployed autonomously in safety-critical applications. They call for further research on establishing capability boundaries, quantifying hallucination risks, and developing reliable detection methods for inevitable hallucinations.